everyone, welcome to HL Chemistry Flip Classroom. In this video we're going to be talking about light, and we'll eventually tie this in and relate it. It is related to atoms, and it is important that we study light in chemistry class, but in the course of this video we're mainly just going to be talking about light itself. Now the first thing I want to show you is this fun little picture here. Now take a look at that a second and see what you think it says. Now if you said light is a wave, you are correct. If this is a W right here. But if you said light is a particle, you are also correct, because that there could be a P, A, R, so forth. What this illustration is supposed to highlight is there's been some debate, or throughout the history of science there was some debate as to whether light was a wave, like a sound wave, like the sound waves you're hearing right now, the sound of my voice, or a wave on the water, or is it a particle? Is there some sort of particle that's traveling along? You know, the issue comes down to people had a hard time understanding. Light seems like a wave in a lot of ways, but waves, typically, sound waves and water waves, they need something to carry them. You know, you can't have a water wave without water, of course. You can't have a sound wave without air or something to transmit those vibrations. So if light is a wave, how does it get from the sun to here, let's say? Well, you know, it turns out that light is a little bit of both. It has a little bit of a dual nature. Depending on how you study it, it can sometimes look like a particle, and sometimes we're going to talk about light in terms of particles, and sometimes it looks more like a wave. For the most part, though, it is really handy just to study it as if it is a wave, and that's what we're going to talk about a lot today. So there's a couple of terms that we need to know, some things that we need to be aware of, kind of some of your standard wave stuff. First of all, we have the wavelength, and these are terms you're probably familiar with or heard at some point. The wavelength is the peak-to-peak distance, or the trough-to-trough distance. Typically we're going to measure that in meters, maybe sometimes nanometers. And then frequency, by the way, the Greek lowercase letter lambda here is the symbol for wavelength, and then frequency, in this font, this is actually supposed to be the Greek letter nu, It's usually a fancy looking V. In this particular font it just pretty much looks like a plain V. But that's frequency. That's the number of waves that pass by a given point in a second. So if this guy was standing here watching these waves go by, the number of waves that passed him by in 1 second is the frequency. The unit for that is hertz. Sometimes that unit is represented as 1 over seconds, like 1 per second. So of course you'll recall when we have a little s to the minus 1 like that, what that really means is 1 over seconds like that. IB will typically always, instead of writing this, they'll always use these negative exponents to represent the units in that fashion. But these two, all three of these things really are equivalent. Hertz, second to the minus 1, or 1 over seconds, those are all acceptable ways to indicate a unit for frequency. So another important wave term is photon. Now a photon is, again, speaking of the particle nature of waves, it's a little bundle of light energy. In fact, one of the weird things about light that's true is basically a photon is the smallest packet of light energy that can exist. It can't get any smaller than that. There is no existence of light energy in any amount smaller than this photon. So you can think of it as a little packet or a bundle of energy. And also the symbol C. This is a relatively famous. It's seen in E equals mc squared and all that stuff. It is the speed of light. The speed of light in a vacuum, which is 3.00 times 10 to the 8th meters per second. Now that is really, 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 really fast. To put it in perspective, it's about 186,000 miles per second. So very, very quick. And as far as we know, that's as fast as it is possible for anything to go, is that particular speed. So it's the maximum speed of light and the maximum speed of anything. Now, Isaac Newton, super smart guy, invented calculus, one of the great scientists of all time. Not only did he do a bunch of work with gravity, but he did a bunch of amazing work with light as well. And he discovered, using a prism, you could split white light up into, he said, 7 colors. Now, Newton was a bit of a numerologist. He had some strange ideas. He thought 7 was a particularly powerful number. That's why he chose 7 colors. He really could have chosen any number of colors, but there's kind of a famous acronym or whatever to help you remember the so-called 7 colors of the rainbow. Roy G. Biv: red, orange, yellow, green, blue, indigo, violet. So you've probably heard that before, probably familiar with that. What I want to make sure that we understand is I want to put this into the big picture of what we call the electromagnetic spectrum. Now, when you are... So stuff like radio waves, microwaves, visible light, X-rays, all that stuff, it's all the same stuff. It's all these photons of electromagnetic radiation that can travel through space. The only difference between them is they have different wavelengths and therefore different frequencies. This particular chart is laid out with the shortest frequencies here on this side and the longest frequencies here on this side. So radio waves have the longest wavelengths, and as we move in this direction, the wavelengths get shorter and shorter and shorter. And as the wavelengths get shorter, the frequency gets higher and higher and higher. It's important to be aware that wavelength and frequency are inversely related. If I'm a little dude over here watching these waves go by, they have longer wavelengths, so the frequency will be lesser. I will see less waves pass by me at a given point than if I was observing these waves. So, again, moving this way, wavelengths are getting shorter, frequency getting higher, visible light. So when it's talking visible light, red has the longest wavelengths and violet has the shortest. So this little part of this is the only part that we human beings can see. There are animals out there that can see in both the ultraviolet and the infrared range. So they have, to their eyes, they have other colors, colors that we just cannot even perceive. And who knows what they look like to them, it's hard to say. So we are going to look at a couple of equations related to light. It's good to have a good kind of big picture feel for this electromagnetic spectrum and kind of how it all fits together. Although there is a copy of it, a similar thing to this diagram in your data booklet. Notice that this one leaves off indigo, so that's a common thing you see these days with only 6 colors rather than 7 of the rainbow. It doesn't matter though. So there's 2 big equations that are important that we're going to use. The first one is C equals speed of light equals wavelength times frequency. So again, we've seen all these letters before already, but just to remind us here and have it in one spot what everything stands for. The next equation is E equals h nu. H is Planck's constant. And we've already seen that this symbol here represents frequency. Planck's constant or Planck's constant, it's a kind of a magic number, if you will, that can relate the frequency of a light wave or a wave of electromagnetic radiation to the energy within that wave. And the higher the frequency, the greater the energy will be. You can see, I mean, if this number is bigger, this number is going to get bigger if we just kind of think about that mathematically. So Planck's constant, it's given in your data booklet. It's one of those numbers you're going to use it a bunch. You'll probably end up kind of memorizing it. Its unit is joule seconds, which is just a way to kind of get the units to cancel out properly. So let's take a look at these one at a time. We're going to start off with the first one. And while you're doing this, please work along with me. What we're really doing is just very, very basic algebra, although people are sometimes intimidated by the scientific notation and work with the scientific notation incorrectly. There's really no reason to be scared of the scientific notation. It's just like any other number. Probably one of the biggest mistakes people make in these kinds of problems is simply putting them into their calculator incorrectly. I'm going to try, if I can, to put a link to another video I have on my channel here on the screen, and so that if you're having trouble, if you're doing these problems and you seem to be, in your mind, punching everything incorrectly and you're still getting a wrong answer, what I would do is take a look at that video and make sure that you're using your calculator correctly. So anyway, it says, what is the frequency of violet light with a wavelength of 4.12 times 10 to the negative 7th meters? Okay, well, this question is asking us for frequency. It's giving us a wavelength. So out of our two light equations, we're going to use this one, because this is the one that relates wavelength to frequency and the speed of light. So just going to do some substitution here. We know C, that's a constant. It doesn't have to be told to us. We know that that's 3 times 10 to the 8th meters per second, and that's a value that's given in your data booklet as well. We were given a wavelength here of meters, so lambda stands for meters. Substitute that in there, multiply by V. Now we're just going to do some basic algebra here. We need to divide both sides by 4.12 times 10 to the negative 7th. Now I can clumsily try to write it here in my little pen, but hopefully you would see what's going on there. Divide both sides by that value. So then we're going to get this. After we divide both sides by 4.12 times 10 to the negative 7th, its frequency is going to be 3 times 10 to the 8th meters per second divided by 4.12 times 10 to the negative 7th meters. Now as far as the units go here, in the top we have a meters per second, and in the bottom we have just meters. So kind of keep that in mind. So do that division, 3 times 10 to the 8th meters per second divided by 4.12 times 10 to the negative 7th meters. And we see that our velocity, if we put it into a calculator right, if we're doing the math right, is 4.28 times 10 to the 14th hertz. And again, please put this into your calculator, make sure you're getting the right answer. Even if the algebra seems simple, just make sure that you double check that. As far as the units go, what ends up happening is this meters that's in the denominator cancels out with this meters that's in the numerator of the numerator, if you will. So then we're left with 1 over seconds, or second to the minus 1 as a unit. So that's where that comes from. Or we can just call that hertz. We can just know that when we're dealing frequency and we find frequency, we should use hertz as a unit. So however you want to get there, any one of those units is fine. We're going to look at another example. What is the wavelength of an X-ray with a frequency of 4.92 times 10 to the 15th 1 over seconds? So it's given us the frequency as seconds to the minus 1 here instead of hertz. But again, it's all the same. So we're going to use this equation, and we're going to substitute in. For C, we're going to put 3 times 10 to the 8th meters per second. And lambda is what we're solving for, wavelength. We are going to put in our frequency here. So that's 9.2 times 10 to the 15th. Now to solve, we got to divide both sides by 9.2 times 10 to the 15th, 1 over seconds. So basically we're going to move this guy here to the other side of the equation. That's what I've done. And by the way, you know, if I'm ever going through these problems too fast for you, just pause the video for a second, get caught up, but rather than sort of rushing through and doing them in real time, take your time, but do make sure you're following the steps as I do them, punching them into your calculator, all of it. It's all part of the skill of getting the correct answer. So when we do that division, 3 times 10 to the 8th meters per second divided by 9.2 times 10 to the 15th seconds to the minus 1. Here, with our units, we got a meters per second in the numerator, and we're dividing that by this. So these two guys end up canceling out here, and it leaves us with a unit of meters. You know, if you struggle with canceling out the units, it's a good idea to look at it if you can, but your other approach is just to remember that in this equation, we're going to get wavelengths in meters, and so we can remember to use meters as a unit when we're finished. By the way, a significant figure thing, that because there's two significant figures in this value right here, we should have two significant figures in our answer. Okay, so there's two example problems. If anything's unclear to you, pop back, watch them again, look at the video to make sure you're using your calculator correctly if that seems to be the issue. But what we're going to do at this time is try one on your own. What is the frequency of a red light wave with a wavelength of 7 times 10 to the negative 7th meters? So please pause the video at this point, work through this problem, make sure you can get to the correct answer. Okay, so hopefully you actually did bother to try this and didn't just sit there and stare at the screen for a few seconds. Last chance to pause it and actually try it. You're about to lose a learning opportunity. Alright, well, I'll show you the answer. Should have come up with 4.29 times 10 to the 14th hertz, or 1 over seconds, or seconds to the minus 1. If you have any problems with that, go back, look at the other problems, try it again, ask me a question in class next time, and see if you can get this figured out. So we got the other equation that we need to look at. But before we do, you know, you guys should be like this cat. This cat is very persistent. I think the dog represents IB. But keep fighting, guys. Keep fighting. Alright, we're going to look at this other equation. Energy equals Planck's constant times frequency. What is the energy of a photon of light with a frequency of 5.3 times 10 to the 14th hertz? Okay, so this is going to be very, very straightforward. We're not even going to have to do any algebra. We're just going to simply plug things into the equation and solve. So we want to solve for energy. That's how I know that I need to use this equation. I'm going to put in Planck's constant. That does not need to be told to you. That number is a constant. It's given in your data booklet. So I know H is that number, so I'm just going to pop that in. And I'm going to multiply it times the frequency. And if we're using our calculators right, and again, please double check, make sure you're getting the correct answer here. We're going to get 3.5 times 10 to the negative 19th joules. So that's the amount of energy in one teeny tiny little photon of this light, which is in the spectrum of the visible light range. So that's a teeny tiny amount of energy, because photons are teeny tiny things. So let's look at another problem. It says, what is the energy of a photon of electromagnetic radiation with a wavelength of 4.91 times 10 to the negative 9th meters? So hopefully, when we look at this problem, something is jumping out at you in that this is giving us a wavelength. This equation necessitates an energy. We don't have an equation. You could maybe figure one out, but we don't have an equation that directly relates energy to wavelength. So what we're going to have to do, and what we can do, is turn that wavelength into a frequency first, because we cannot use this equation with a wavelength. So I'm going to use the first equation, and I'm going to turn that wavelength into a frequency to give me something that I can use in this equation. So substitute in speed of light, put in my wavelength here, 4.91 times negative 9th, I'm going to solve for frequency. Now, I'm hoping that you have kind of caught on and you can do that, so I'm going to kind of skip just to the actual answer here. Solving this little guy for frequency, I get 6.11 times 10 to the 16th hertz. So now that I know that frequency, then I can use this equation, and I basically just need to multiply that frequency times Planck's constant. So popping in Planck's constant here, popping in the frequency here, multiply the two together, we get 4.05 times 10 to the negative 17th joules. Unit-wise, what ends up happening here is joule seconds of the energy. Remember, hertz is the same as 1 over seconds, right? So this second here and this second cancel out, which gives us joules as a unit, and that's a good unit for energy because joules are a unit of energy. Okay, so sometimes these two-step, two-equation problems can get a little bit tricky. You know, if you had trouble, pause, go back, watch it again, see if it makes sense to you. I'm going to give you another chance to practice here in just a second. So what I'd like you to do is take a look at this problem. It's very, very similar to the last one, but see if you can work through this problem and arrive at the correct answer. Okay, so I'm sure, since you're all wonderful little IB students, you actually did pause it and try this before waiting, but let's take a look. So again, it's going to be a two-step process. We're going to have to use one equation and then the other. First, I am going to solve, since we have the wavelength, I need the frequency. I got to figure out the frequency first. Plug in my numbers, solve for frequency. I get 3.9 times 10 to the 11th hertz. Once I have the frequency, plug it into this equation. Basically, just multiply times Planck's constant. Frequency times Planck's constant is going to give you the energy. We get 2.6 times 10 to the negative 22 joules. So, you know, from that, from a few different things, I can tell this is a longer wavelength of types of radiation and a lower energy than the last one we saw. This would not be in the visible light range. In fact, if we look at this value, this wavelength, let's discard those. If we look at that wavelength at 10 to the 14th meters, and just for kicks, we're going to go back and look at this electromagnetic spectrum again. So we can tell, actually, here's our wavelengths on the top. This must be in the infrared range. So that particular photon that we were just looking at would not be something that would be visible to humans. Alright, ladies and gentlemen, that's about it for this episode. Thanks for watching. We'll see you soon.